Hello everyone. Please note that this is a NotebookLM video presentation. Thank you NotebookLM. Hope you find it useful.
So we're going to tackle a huge question today. We're diving deep into two of the most complicated things in the known universe, artificial intelligence and, well, the human brain. And it turns out a recent paper has given us this kind of mind-bending new way to think about how they just might be connected. You've heard this phrase a million times, right? We talk about advanced AI as a black box. We see what goes in, like a question you type into a chatbot, and we see what comes out, the answer it spits back. But the whole process in the middle, how it actually gets from A to B, it's murky. It works, but we don't really truly know why.
And that, of course, brings us to the ultimate black box. For all the amazing progress we've made in neuroscience, the human brain is still this profound mystery. We know it's where our thoughts and memories and us comes from, but the nuts and bolts of how it all works, that's still the frontier. So what if these two black boxes aren't so different after all?
All right, so to peek inside these boxes, we first got to understand the two main theories for how a complex system, whether it's made of silicon or cells, processes information. It's really a tale of two very different-looking ways of thinking.
Now, the key idea for both theories is something called a generative model. Just think of it as a little model of the world that you build inside your head. Both AI and our brains create these internal models to figure out how things work, to understand cause and effect, and most importantly, to guess what's going to happen next. But how they build that model, well, that's where the two big ideas split.
So, on one side, you've got the deep temporal model. This one is all about hierarchy. It tries to understand the deep, underlying reasons for things. The best analogy is a company's org chart. It's all about structure and who reports to whom. It values depth. Then, on the other side, you have the autoregressive model. This one is flat. It cares less about the why and way more about what's next. It just looks at everything that's happened before and predicts the very next thing, kind of like a great jazz musician improvising the next note. This one values width. For years, the debate was basically, which one is right?
But here's the kicker. What if that's the wrong way to even think about it? What if they're not actually competitors? This is where this whole idea of closing the box comes into play, and it reveals this absolutely stunning mathematical twist.
Closing the box isn't just a cool phrase, it's a real mathematical thing called marginalization. Now, don't worry about the term. All it means is that you can take a complex model with all these hidden internal layers and variables, and you basically sum them all up, you integrate them out. And when you do that, you transform the model into something that looks different, but, and this is key, it works in the exact same way. So check this out. This is what it looks like in practice. You start with that deep model, right? It's got that clear hierarchical structure we talked about. Then you do the math. You close the box, collapsing all those internal layers. And what do you end up with? Boom, the wide autoregressive model. It looks completely different, but here's the mind-blowing part. It makes the exact same predictions. So this is the whole point. This is the big takeaway. These two models, the deep causal one and the wide predictive one, they can be just two different ways of looking at the very same thing. They're not fighting each other for the crown. One can literally be mathematically transformed into the other. It's like two different languages describing the same object. Okay, so what? Why does this matter? Well, this idea has absolutely huge implications for how we understand our own minds and the artificial ones we're trying to build. Let's break down what this means for brains, bots, and everything in between.
For neuroscientists, this is just beautiful. Because, you see, we know the brain has a hierarchical structure where information gets processed in stages. That fits the deep model perfectly. But we also see these incredibly dense, sprawling connections within those layers. That's called lateral connectivity. And that fits the wide autoregressive model. This theory just elegantly solves the puzzle. It says our brains aren't choosing one or the other. They might be running a deep model using a system that, from the outside, just looks like a wide one.
This, of course, brings us right back to AI, especially the transformer models that are behind everything from ChatGPT to Midjourney. If these two types of models are just two sides of the same coin, then what is the AI actually learning when we feed it the entire internet? Is it learning the deep rules of the world, or is it just getting really good at spotting surface-level patterns?
The paper makes this really critical distinction. Learning the deep generative model means you're learning the parameters, the actual cause and effect rules of how something works. But learning the wide autoregressive model, that means you're just learning the kernels, which are basically a cheat sheet for input-output relationships. It's the difference between knowing the laws of gravity versus just knowing that if you let go of a pen, it drops.
And this gets to the paper's core hypothesis about today's AI systems. Transformers might be getting unbelievably good at learning those autoregressive kernels. They can map data to data with spooky accuracy, predicting the next word in a sentence better than any human could. But they might be doing all of this without ever learning the deep generative parameters, the actual why behind it all. In other words, they are masters of mimicry, not necessarily masters of understanding.
Which brings us to a final and honestly pretty profound point about the very different goals of science and engineering. It's all about whether you want to open the box or just keep it closed.
I mean, just look at this table. For an engineer, the goal was often to close the box, right? What really matters is performance. If an autoregressive model works great and scales up, who cares if it's a black box? The result is king. But for a scientist, the whole goal is to open the box. Scientists want to get in there and understand the mechanism, to figure out the causal, generative model hiding inside. For them, transparency is everything. This quote from the paper just nails it. It says that even if an AI works perfectly, as long as it's a closed box, it's still a black box from a scientific point of view. We can't actually understand the fundamental principles of intelligence just by building better and better prediction machines. To do that, science has to pry the box open.
And so that's the thought I want to leave you with. As we build these more and more powerful AIs that can mimic human intelligence almost flawlessly, we have to ask ourselves, if we succeed, if we build the perfect black box, one whose inner workings are a total mystery to us, have we really solved the puzzle of intelligence? Or have we just created an even bigger one?